next we are having a valence shell electron pair repulsion theory. The valence shell electron pair repulsion theory, which talks about the shape of a molecule or the change in a shape due to the pair of electron which is present in a outermost shell. Now here we are talking about the electron pair which is present in a valence shell of the central atom. The theory name is valence shell electron pair repulsion theory. That means valence shell, that is electron pair from the valence shell, and the repulsion. So here we are talking about the repulsion, the things which are happening because of the repulsion between the electron pair present in a valence shell. Now what valence shell electron pair repulsion theory says? It states that, again it have a certain postulates which states that that the shape of a molecule is decided by the electron present in a valence shell, electron pair present in a valence shell of the central atom. That means if there is a 4 pair of electron in the valence shell, then those 4 pair of electrons will decide that what is the shape of the molecule. Then here the electron present in the outermost shell, the valence shell of an atom, may be of two types, because for example, suppose I did methane molecule hybridization, in which we observe that in methane molecule the carbon is having 4 unpaired electron and 4 unpaired electrons shared with the 4 hydrogen atom. But in case of ammonia, there was a 4 orbital sp3 hybridization, but out of 4 orbital, 1 orbital was completely filled and the remaining 3 was half filled. So in case of ammonia, so the remaining 3 was going to be, they will form, so those remaining 3 will form a bond, and that one which is left is going to be called as a lone pair electron. For example, let's see the example of ammonia, and on the basis of this we are going to learn about the valence shell electron pair repulsion theory. So ammonia, where the nitrogen is a central atom whose atomic number is 7, so its electronic configuration as we know, it's a 1s2, 2s2, 2p3. So have 2 electron in the outermost shell in a 2s orbital and the 3 electron in the p orbital, that is px, py and pz. The nitrogen undergoes hybridization state. Here there is no need of writing the excited state. The reason, because already all the electrons are already the ammonia, we are talking about the formation of ammonia. In ammonia, nitrogen forms 3 bond, and here we are having 3 half-filled orbitals. So no need of writing excited state. Hybridized state. In hybridized state, what happened? It's a 1s2. Okay, in hybridized state, so electron present in the outermost shell, whatever the orbitals we are having in the outermost shell, they all are undergoing mixing and recasting process, and they form 4 new orbitals. The electron distribution in 4 new orbitals will be same, and each orbitals are called as sp3 hybrid orbital in this case. So here the nitrogen forms 4 sp3 hybrid orbital. Now the case of hydrogen. Hydrogen, whose atomic number is 1, having a 1s1 configuration, that is 1 electron in 1s orbital. Now what happens in case of ammonia? In case of ammonia, that is NH3 molecule, this is the central atom. The geometry or the properties generally depends upon the central atom. So here we have 4 orbitals of the nitrogen, out of which 1 is completely filled. These 3 are half filled. Now in case of ammonia, what will happen? The hydrogen atoms, each hydrogen is having 1s orbital. So first hydrogen 1s orbital will overlap here, second hydrogen 1s will overlap here, and the third 1s will overlap in this case. So now this becomes ammonia molecule, and in ammonia molecule, this is nothing but the valence shell configuration of central atom, that is nitrogen. So according to the valence shell electron pair repulsion theory, the shape of a molecule depends upon these electron pairs which is present in a valence shell of the central atom, that is, for example, here it is nitrogen. Here we are having 2 types of electron. The one is called as a bond pair and the second is called as non-bond pair. Non-bond pair, that is called as a lone pair electron. So here we have 2 pair of electron, 2 different types of pair of electron. The one is called bond pair and the second is called as lone pair of electron. The lone pair of electron, that is a pair of electron which is present in an outermost shell but doesn't take part in a bonding, and the bond pair, that is a pair of electron which has been formed, or here the pairing has taken place due to the bonding of due to the overlapping of the 2 different orbitals. Then rule number 2, these all 4 orbitals which are present in the outermost shell of the nitrogen, in the ammonia molecule. Since they all are having a pair of electrons, so they all are having a same charge, and that's why they always repel each other. So these all four orbitals are repelling each other because of the same charges, and during the repulsion its stability goes on decreasing, so they repel. So these orbitals orient themselves or fix themselves in such a way that the distance between these orbitals should be maximum. They should be the maximum away from each other, and so that I can say that the repulsion will be minimum. So just to reduce that repulsion, they are always far away from each other as much as far it is possible, so that the repulsion should be minimum. And if the repulsion is a minimum, it means the energy will be energy of the molecule will be minimum and the stability will be maximum. Now here in the case of, we have the 4 pair of electron, but in case of 4, that is 1 is a lone pair and the 3 is a bond pair. So we have 2 types of pair of electron. Here the repulsion produced by the lone pair electron and the bond pair electron, the repulsive forces exerted by the lone pair and bond pair electrons are different. The lone pair electron generally produces more repulsive forces, means it produces more repulsion compared to the bond pair electron. If suppose there is a 2 or more bonds are forming, there is a double or triple bond is forming, then there is a 2 or more than 2 pair of electrons are there, and in that case those 2 or more than 2 pair of electrons are considered as a super pair of electrons. In the case of this, as the bond angle, that suppose during the formation of a molecule, once the molecule is formed, so in a molecule, as the bond angle, that is the bond angle increases, that is the distance between the 2 bonds increases, means the 2 orbitals are moving away from each other. So as the bond angle increases, I can say that here the repulsive forces goes on decreasing, because if the bond angle increases, means 2 orbitals are moving away from each other, and if 2 orbitals are moving away from each other, that means the repulsion between them will goes on increasing. For example, suppose if the bond angle for any bond is 90 degree, then repulsive forces will be more. Comparatively 120 degree angle, the repulsive forces will be less. If the angle is 180 degree, then the repulsive forces compared to the 90, it will be very, very less. So this is about the valence shell electron pair repulsion theory, according to which these pair of electron decide the shape of a molecule. These are the pair of these or I can say the repulsion between these pair of electron decide the shape of a molecule. For example, let's talk about the ammonia. Ammonia, it undergoes sp3 hybridization. So rule says that it should be a it should have a tetrahedral geometry with the bond angle 109 degree. But while studying hybridization state, we saw that the bond angle, or we learned that the bond angle of the ammonia, in case of ammonia, decreases. Instead of 109 degree, it is 107 degree. Why? Suppose this is the ammonia molecule, nitrogen at the center, it have a 1 lone pair electron, this is with hydrogen, that is another pair of electron, this one. There is a 1 more lone pair electron, that is this one, and this is the 3rd lone pair of electron, that is this one. So here in the case of this, I can say in case of ammonia, this being a lone pair electron, these all 4 orbitals are repelling each other, but the repulsion produced by the lone pair orbital is more compared to the bond pair. So here the repulsion, in this case the repulsion is more, here also the repulsion is more. So this repulsion is more than these 2 repulsions. So ultimately what happens, that is lone pair bond pair repulsion, lone pair bond pair repulsion is more than bond pair repulsion. Here we have an order, lone pair repulsion is more than lone pair bond pair repulsion is more than bond pair repulsion. So here we are having lone pair bond pair, these 2 are bond pair. So lone pair bond pair repulsion is more compared to these 2, and due to which what happened, this bond angle decreases, and the bond angle, instead of 109 degree, it becomes 107 degree, 18 minutes. So ultimately what happens, because of the repulsive forces present between the orbitals, the shape of the ammonia has changes. The shape, for being a regular tetrahedral geometry, its angle should be 109 degree, but it has decreases to 107 degree. It means now it will be called as a distorted tetrahedral geometry. So here the shape of ammonia molecule changes only because of the repulsive forces present in the electron pair in the outermost shell. Then second, we did for the water molecule. In case of water molecule, we studied that there was 2 lone pair of electron, water molecule, that is oxygen at the center. The two lone pair of electron was there. So the first lone pair electron, second lone pair of electron, and this is first hydrogen and second hydrogen. Now in case of water molecule, here the lone, we have all the three types of lone pair, lone pair, lone pair, bond pair, lone pair, bond pair, and bond pair, bond pair. So here the repulsion is maximum between this lone pair, lone pair. So ultimately they will move far away from each other. The effect of this will fall on this lone pair and bond pair. Due to, if they are moving away from each other, then ultimately these two will repel these two. So ultimately the whole effect is getting, whole repulsive forces are getting on this bond pair, because the bond pair repulsion is the weakest at repulsion. So here ultimately this will contract, and this will contract means instead of bond angle, again water, in case of water, oxygen again undergoes sp3 hybridization. So here I can say, since the lone pair bond pair repulsive forces are stronger than bond pair repulsion, therefore this bond angle again reduces, and it reduces to 104 degree and 35 minutes. So again I can say that the value reduces, the bond angle changes. Bond angle changes, that is somewhere the geometry of the molecule has been also changed, and these all thing is happening only because of the lone repulsive forces present between the electrons in a valence shell of the central atom. Let's say 1-2 more example for where the shapes of a molecule changes because of the presence of the lone pair. The next is ClF3 molecule we are having. ClF3 molecule where chlorine is a central atom whose atomic number is going to be 17, and still outermost shell configuration I'm just writing 3s2 3p5, means have 2 electron in a s orbital and 5 electron in a p orbital. Okay, chlorine have only one half-filled orbital, but the rules, but here in a molecule ClF3 it is forming a 3 bond, so there should be 3 half-filled orbital. That means there will be a one more orbital, that is 3d orbital. Currently no electron in a 3d orbital. So here the one electron will excite from this to this, and if one electron is excited, so the chlorine 17 in excited state, it will become 3s2, 3p5 will become 3p4 now, and then this is 3d1. So S is having 2 electron again, P is having 4 electron now, and the D also have 1 electron. So now the chlorine undergoes sp3d hybridization. So in hybridized state, sp3d, that is S, 3 orbital from P and 1 orbital from D. So it undergoes sp3d hybridization, and so we have 5 new orbitals formed. The distribution of electron will be same. The first 2 orbital will have pair of electron, while the other 3 will have a half-filled electron. So here these 2 pair of electron is a lone pair, and since they are half-filled, so these 3 are going to form a bond with fluorine atom. And if these 3 will form a bond with the fluorine atom, that means this, and it will, so that it will become a bond pair electron. So ClF fluorine atom, fluorine whose atomic number is 9, its electronic configuration, outermost shell configuration again 2s2 to p5, means have first all electrons singly and then pairing will take place. So here again we have, so fluorine, the fluorine being a peripheral atom, it will not undergoes the hybridization process. So directly from the, I can say from fluorine who will form a bond, then the answer is pz orbital. And if pz orbital is forming, then the status of ClF3 molecule is, it will become five orbital, 2, 2, and these 3 electrons are from the chlorine. Now, from the fluorine, first fluorine pz orbital will overlap here. We have total 3 fluorine. Second fluorine p or pz orbital will overlap with this chlorine, with this unpaired electron. Third fluorine will overlap here. So I can say that these 3 pair of electrons are bond pair, while these 2 are called as a lone pair, as they are pair of, as these are the pair of electron but doesn't take part in a bonding. Okay, so the shape of ClF3 molecule, Total 5 electron pair, and if it is a 5 electron pair, then the shape will be trigonal bipyramidal. Trigonal bipyramidal, it means the shape is something like this. This is a trigonal bipyramidal, and these are the other two. That means these two are the pair of these three are in a same pair, and these two are perpendicular. And but out of these 5 pairs, so 1 pair, 2, 3, 4 and 5 pair, but out of these 2 pair, 2 are lone pair. So being a 2 are lone pair, here 1 pair, second lone pair, this will be fluorine, this is also fluorine, and this is also fluorine. Now what will happen due to the presence of this lone pair electron? The lone pair repulsion is more, and due to this more repulsion, what will happen? This fluorine atom will slightly shifted toward this fluorine atom, so that ultimately where it's a perpendicular, the rule says that it should be perpendicular, that is a 90 degree, but due to the more repulsion between the lone pair orbital, it slightly gets slanting condition, and we get Cl, fluorine, this is the second fluorine, and this is the third fluorine, and here we are having 2 lone pair of electron. The expected bond angle was 90 degree, but now it becomes 87.5 degree. That is the value decreases in case of ClF3 molecule. The next is, suppose if I have BrF5 molecule, bromine pentafluoride. Now what happens in case of BrF5 molecule? Bromine, whose atomic number is 35, outermost shell configuration is 4s2 4p5. So we'll have 2 electron in s orbital and 5 electron again in p orbital for singly, and then pairing will take place. Bromine is forming a 5 bond, but here in this case we have only 1 half filled orbital. That means the 4d orbital will also take part in a bonding. Okay, now the excited state, bromine 35. In excited state, let's see what will happen. Electron from this will excite to this, so we will have 3 half filled orbital, but I require 5. So from this also the one, that is these two, both the electron from both the orbital will excite. So we will have 4s2, 4p will have now 3 electron only, and this is 4d will have now 2 electrons. So 4s2, 4p3, and 4d is also having 2 electron. So now the bromine undergoes sp3d hybridization, sp3d2 hybridization. 1, 2, 3, 4, 5, 6. 6 orbitals are overlap, undergoing mixing and recasting process. So 6 new orbitals will form. So 1, 2, 3, 4, 5, 6 new orbitals. Electron distribution will be same. 1, here also 1, 1, 1 and 1. So I can say that now here we have the 5 half filled orbital and the 1 lone pair of electron. So again lone pair of electron is there. So again repulsive forces is going to disturb the shape of the molecule. Now it is a BrF5 molecule. BrF5, that is here. Bromine. This is the condition of a bromine. Now fluorine, as we saw here, each fluorine atom have 1 lone pair of electron. So fluorine will combine together. Fluorine, the first fluorine pz orbital will overlap here, second fluorine, third fluorine, fourth fluorine and fifth fluorine. So now this is BrF5 molecule. These 5 are called as a bond pair, and this is called as lone pair. So again the lone pair and bond pair both are present, so the shape will get disturbed. It's a BrF5 molecule, total electron pair is 6, out of which 1 is a lone pair and the remaining 5 is bonded with the fluorine atom. If there is a 6 electron pair, then geometry is a octahedral geometry. Octahedral geometry means this is the central atom and the one is here and the one is here. This is the octahedral geometry, means fluorine, 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 and this is also fluorine, and this is going to be a lone pair electron, and bromine will be at the center. Now what will happen? All angles are expected to be 90 degree, but what will happen in the case of this? Now let's see. Br, first fluorine atom, second fluorine atom, third fluorine atom, 4th fluorine atom. Here we have 5th fluorine atom. And here we have lone pair of electron. Again, due to the presence of lone pair of electron, so now there is only, this is the shape. We have this shape. So ultimately this is called a BRF5 molecule. That is, here I can say that there is a pair of, this lone pair of electron produces the repulsion, and there is a no bond, so this will not take, doesn't decide the shape, it's just changes the angle. So it is going to be a square pyramidal. That is, a square is a base, and if I am joining all the points, then it will form a pyramidal shape. So this is about the valential electron pair repulsion theory. That is how it changes the shape of a molecule due to the repulsion between the atoms, the electron pair present in a valence shell. The lone pair, if there is a lone pair electron, then it changes the shape of the molecule, changes the bond angle, and etc. Valential electron pair repulsion theory. Now let's see the shape of the certain molecule in which the central atom is having one or more lone pair of electron. So one or more electron pair, that is one or more lone pair electrons are present. Now what will be the shape of the molecule depends upon that how many pair of electrons are there in a molecule. Suppose if there is a 3 electron pairs. If there is a 3 electron pair, then there will be a 3 possibility. The possibility number 1, either the molecule will be AB3 type, or it is going to be AB2 type, AB2 and L, and okay, there will be only 2 possibility. AB3 and AB2L type. Now AB3 where A stand for the central atom and the B stand for the peripheral atom. And if I am writing a L, that means it is a lone pair of electron. So if there is A is a central atom, it is having a 3 pair of electron, and 3 pair of electron is bonded with the 3 bonds. It means here there is a no lone pair of electron, all electrons are bond pair. And if all electrons are bond pair, then the shape is going to be something like this. A will be at the center, one B atom here, the second B atom will be here, and the third B atom is here. So ultimately I can say that this shape is a trigonal planar geometry. This is trigonal planar. The example here I can say the BF3 molecule. The BF3 molecule is the example for this. Second is a AB2L type. AB2L type means where one electron is a one electron pair. There is again 3 pair of electron, that is, suppose if there is A is a center, 3 pair, 1 pair, second pair and third pair. Out of 3 pair of electron, 1 electron pair is a lone pair. So this is the lone pair electron here. And this is another electron pair, this is another electron pair which is forming a bond. So if I am talking about the shape, see this is an electron pair, that means here I can write this electron pair can be written like this also. That means it doesn't decide the shape, it does due to the repulsion, it decide the shape only because of its repulsion. So there is only 2 bond, and the shape of the molecule is something like this, A and B. And there is a lone pair electron. So I can say that this shape is nothing but what it is, a V shape or bend shape. So the shape of the molecule is, here I can say V-shaped molecule, this is, okay. The example I can say SO3 molecule, O3 molecule, these are V-shaped molecule. Then next is, if there is a 4 electron pair, then what happens? Total electron pair are 4. If 4 electron pair means it is forming a 4 bond. The first one is AB4. The second is AB3L. And the fourth is AB2L2. Okay. AB4. AB4, it means there is A is a central atom and all are bond pair. There is no lone pair of electrons, so 1B will be here, second B, third B, and this is the fourth B. This is called tetrahedral geometry. That is, the shape is tetrahedral. The example I can say methane molecule, ethane molecule, butane, propane, all alkanes comes under the same category. AB3L molecule, that is a 1 electron is there is a 1 lone pair electron and the 3 bond pair electron. 3 bond pair electrons, so A is at the center. This is going to be a lone pair electron because there is a one lone pair. B, and there is a third B. This is called pyramidal shape. Pyramidal shape which is observed in case of ammonia molecule. That is, example is ammonia. Ab2L2 type. Now in case of Ab2L2 type, so let him drawing here the diagram. A will be the center, one lone pair. A will be the center, one lone pair is here, there is a two lone pair, there are another lone pair here, and we have B atom here and the second B, that is this one. So again there is a two lone pair electron and there is only two bonds, so it appears like this. So I can say that it is again a V shape or bend shape or also known as angular shape. Here example I can say H2O molecule. In case of H2O, the central atom oxygen is having a two lone pair of electron, but in case of SO3 molecule, the central atom S is having only one lone pair electron. So not SO, this is SO2, sorry, not SO3. The next is 5 electron pair. Five electron pair. Now let's see what are the different possibilities in this case. AB5, one lone pair electron, that is AB4L. AB4L2 and then AB3L3. AB2L3, AB3L2. Okay, so these are the five possibilities: 5 pair, 4-1-5 pair, 3-2-5 pair, 2-3-5 pair. Okay, now AB5. If it is a AB5, then what will be the shape? So A will be at the center. All 5 are bond pair. So one bond will be here, B. This is another B. This is another B. And there is a one B which is axial angle, which is forming angle like on axis. This is called as trigonal bipyramidal geometry. And we had learned about this geometry in PCl5 molecule. That is, example is PCl5. AB4L. AB4L, it means out of these 5, one is going to be a lone pair electron. So this is a lone pair electron. This is the lone pair, and that is the geometry will be something like this. A, and this is B. The example for this I can say, this is called seesaw structure. Seesaw geometry, the example is SF4 molecule, where the sulfur will be at the center, fluorine, 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 and this will be the lone pair electron. The sulfur have 6 electrons in the outermost orbit, out of which only 4 is using for the bonding. So that is one pair of electron will be left. Then third example, AB3L2. In case of AB3L2, A is again a central atom. And there are 3 bonds. These 3 bonds are like 1, 2 and 3. Lone pair, one lone pair, second lone pair. This is called T-shaped geometry. And we just saw this structure, that is in case of ClF3 molecule, T-shape. Then AB2L3. AB2L3, that is where 3 lone pair of electron we have. So A at the center, these 3 lone pair electron, 1, 2 and this is 3. So there is only two bonds, this bond and this bond. So ultimately this geometry is going to be, if someone is asking me the bond angle, then BAB bond angle, this is 180 degree. And being a 180 degree, this is linear geometry. This is linear geometry. Now in the case of, see, generally just keep in there is a small trick I can say, that how to know which orbital will occupy the lone pair and which will occupy the bond pair, this electron pair. The orbitals which are present at a higher angle, always the lone pair electron occupy those orbitals which are present at a higher angle. For example, in the case of this AB5, I can say we are having a two different angle. This angle is 120 degree and this is perpendicular, and being a perpendicular it is 90 degree. This is also 120 degree, this is also 120 degree, but this two. So you can see that these two are forming a 90 degree angle. So in all and these three are forming a 120 degree angle. So if the lone pair is replacing, then the role pair occupies only these three positions. It is not occupying these two positions because the repulsion between them is maximum, so orbitals are far away from each other. So they always occupy the orbital which is present at a maximum distance from each other, that is at a higher angle. So in this 120, the same trigonal planar geometry, that planar angle, planar part. No case I can say that the electron is occupying these two axial positions. These are called equatorial position and these two are called as axial position. So since axial position is forming a small angles, so it is always occupied by the bond pair, not lone pair. Okay, this is about the 5 electron pair. Suppose if there is a 6 electron pair, then what will happen? There is a 6 electron pair now. If there is a 6 electron pair, we have three possibilities. Number 1, AB6. Number 2, AB5L. And number 3, we have AB4L2. If it is AB6, then geometry is A is at the center, all are bond pair, one B atom here, one B atom here, the next B atom is here and the next B atom is here in this case. So these B atom, these four bond pairs are in a same plane, that is they are equatorial again, and there is a two bonds which are perpendicular to this plane. That means if A is the center, one B will be at this corner, one B will be at this corner, one will be at this corner, one B will be at this corner. The fifth B will be the perpendicular like this, and the sixth B will be again a perpendicular from the back side. So here I can say this is B and B. In this case all angles are 90 degree. All angles are 90 degrees, so I can say that lone pair electron can replace any of the 4 or any of the 6 electron pair. AB5L. This is called as square bipyramidal geometry. Or also known as octahedral geometry. So we have square bipyramidal geometry or octahedral geometry. Why it is called square bipyramidal? The simple example as I say, suppose A is here, 1B, 2B, 3rd B and 4th B. They form, that is all 4 B's forming a square shape. 1B is present here, and if 1B is present here, then if you are joining all 4 corners with this B, then ultimately a pyramid will form. And the same thing will happen on the back side also. That means we are getting a 2 pyramid, one is toward my side and the other is the back side. So ultimately, and the base is squares. That's why square bipyramidal geometry or octahedral geometry. AB5L, A is at the center. This is B, B and B. One is an electron, one is a lone pair electron. So this lone pair electron is suppose here, and the 5th B. One is electron pair. That means now we are having only 5 bonds, 4 at the corner and 1 is here. So I can see here we are getting a pyramidal shape. There is no such pyramid will form on the back side because there is no such atom on perpendicular to the back side. Okay, so here we have only one pyramid, base is same, that is a square. So the geometry is called as square pyramidal geometry. Square pyramidal geometry. Example for this I can say SF6 molecule. The example for this I can say BRF5 molecule. BRF5 molecule. For this example I can say XEF2 molecule. Xenon fluoride. Xenon will be at the center, one fluorine, and the remaining 3 lone pair electrons will be here. The next, AB4L2 molecules. If AB4L2 molecules means A is at the center, one fluorine B, second B, third B, and fourth B. One lone pair is here, one lone pair is here. Sorry, lone pair. So like this, lone pair. So now, on both the side there is a lone pair. So we are having only a square, that means a square planar geometry. This is called square planar geometry. And molecular formula is XCF4. So these are the shapes. If it is having a 6 electrons, there is a one more molecule, that is we have one more structure, that is AB7. AB7, so it have tetrahedral, it have a trigonal bipyramidal geometry where A is at the center. The 2 boron atoms are here. One boron atom is here. And in this case, we are not having a lone pair electron. This boron is something like this here. So we have this geometry. That is in the case of IF7. One is here and the one is here. That is, this is called as trigonal bipyramidal geometry. Trigonal bipyramidal geometry. The example for this, I can say that IF7 molecule. So what will be the shape of a molecule? It totally depends upon that how many electron pairs. This is the simple shortcut or the trick I can say which we can use for remembering the molecules, where the lone pair and where the bond pair will be present, and what are the different possibilities. Just write like the 3 electron pair, 4 electron pair, 5 electron pair, and 6 electron pair, and what are the different possibilities. Here we cannot have ABL4. The reason, because if there is only one bond pair, the shape cannot be decided and such molecules are not existing. So here we have AB2L3, 6 electron pair, we have 3 in a syllabus, and for AB7 we have only there is no lone pair electron. So this is about the shape of a molecule having one or more lone pair electron. The many time in the exam they give the molecule and the question is asked what will be the shape of a molecule. So suppose if I wanted to know the shape of molecule, for example, suppose they can ask what is the shape of xenon tetrafluoride. Then if it is a question on xenon tetrafluoride, then how to solve? So here I know that the xenon is having atomic number, xenon being a noble gas, the outermost configuration will be S2 and P4, S2 and P6. S will have 2 electron and P will have 6 electron. Okay, or simply I can say that xenon tetra, so 6 electron means from this how many electron pair will be moved out? 1 electron pair and second. So that here I will get 2 electron pair and 2 more electron pair. Still there is a 2 lone pair electron. Hybridization, it will be S, P3, and these 2 electrons which are migrating, it will migrate to D orbital. So we will ultimately have sp3d2. sp3d2 means how many electron pair? 1, 2, 3, 4, 5 and 6. So 6 electron pairs. So here we will have 3 options. Okay, out of this also there are 2 lone pair electron, and 2 lone pair electron means this is going to be the geometry of the xenon tetrafluoride. And similarly I can write the geometry of each and every molecules which are written here by using its electronic configuration.